This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions of software engineering topics at least once a month. SE Radio is brought to you by IEEE Software Magazine, online at computer.org/software.
Flavio Junqueira, thanks for coming on Software Engineering Radio.
Yeah, sure. Nice talking to you, Jeff. Thanks for inviting me.
Yeah, so today we're going to be talking about Apache ZooKeeper and I guess you could call it distributed coordination. So why don't we start off by talking about what is the purpose of Apache ZooKeeper? What problems does it try to solve?
This is a very interesting question because ZooKeeper is related to what I would say meta operations of a cluster. So you have a distributed application. It has a number of servers running your application. And there are a number of operations that you have to do that they're not necessarily related to the application directly, but you need to do them to get your cluster going. For example, you might need to elect a master among a group of servers. And the end user is not gonna know that there is a master, but for the application to run correctly, you need to elect that master. And so ZooKeeper helps you with those kinds of tasks. And when I mention clusters, you can think of clusters of pretty large clusters, say hundreds or thousands of servers, trying to do this kind of coordination. And although I use master election as an example, there are many of these tasks that are sort of common when you're trying to implement a distributed application. You can think of things like group membership. You want to know which members of your cluster are actually up, right? So if you have hundreds of servers running, it might be the case that a small fraction of those are not up at a given time. You'd like to know who they are so that you can make assignments accordingly. A pretty common use of ZooKeeper is also metadata management. Right? So you need to store some metadata reliably. You need that metadata to be distributed across the cluster in a consistent manner. And so ZooKeeper helps you with all that.
And so there's this Airbnb tech talk that I watched about ZooKeeper, and it features Patrick Hunt, and I'll put it in the show notes. But so he talks about ZooKeeper, and he frames his discussion in terms of fallacies about distributed computing. And these sorts of fallacies that he listed were like, you have a reliable network, there is zero latency, infinite bandwidth, you have no problems with security, there's no changing network topology, and all these things are not actually true in your typical distributed system. There's some kind of problem that violates one of the fallacies that I just mentioned. So is it reasonable to look at ZooKeeper as a patch for these fallacies, like a way of sort of eliminating them so you don't have to think about them as much?
The way I look at those fallacies is what developers end up doing in their code when they try to implement the tasks I was mentioning before in a quick and dirty manner. Right? So it's not that people actually make those assumptions that the network is reliable, there's zero latency and so on, but if it's not your main goal, right, to implement those tasks. If your task is to implement, I don't know, a crawler or a data store or something, odds are that you try to do these tasks like master election, group membership, and so on in a quick and dirty manner. And so you end up simplifying your code and having the problems that those fallacies are actually alluding to. I prefer to look at ZooKeeper not as a patch for those things, but more of a structured and natural way to look at the problem. So it gives a way to developers to reason about these problems in a much more natural way, which leads to more robust implementations.
So let's kind of think about, or I kind of want to discuss it from the point of view of a typical user. So for example, let's say I'm a user that has designed some application that is, like you said, that treats these issues, these fallacies, as just non-existent, and I, let's say I built the way that I built my application was quick and dirty, and I wasn't really considering the fallacies. So how am I going to start using ZooKeeper to solve these problems. I have this collection of distributed systems problems, and I want to sort of collect all of them in a single context or look at them through a single lens. And I guess that lens would be ZooKeeper. So how do I start using ZooKeeper to manage those issues across my application?
There are 2 points for beginners, I would say. One is to look at the API. The API is actually very simple. The core API is very simple, has 6 calls. It allows you to manipulate these small files that we call znodes. You create them, you can read them, you can change their data. And once you're familiar with the API, which shouldn't take very long, it's again only 6 calls, it's good to go and look at recipes. So recipes are these ways of using the API to implement the various tasks that people care about. So synchronization primitives like locks. If you're trying to do master election, there has been a number of implementations out there of master election on top of ZooKeeper. And so I think that this is a pretty good way of going about it. So understanding the API, or at least have a cursory understanding of the API, and then go learn from the recipes, because there is just a lot of experience out there.
So let's say, for example, like I'm developing a game, and the game has shot up in popularity, and I wasn't prepared to scale, and I'm starting to scale now, and so it becomes this huge distributed problem, and I realize I want to use ZooKeeper because I've heard of it as a solution. So could you maybe outline what a recipe would look like, or what am I going to start? So I have znodes in ZooKeeper. What am I going to start to be doing with those znodes?
Yeah, so you can, for example, have metadata of a user stored in ZooKeeper. Or in fact, for all your users, you can have, say, one znode containing their metadata. And the metadata could be the profile of the user plus the scores of the user, or the status of the user for a given game, what level the user is at some point, or how many points it has scored up to now. So that could be a way of doing this. Other things, and to be very honest, I've never tried to apply ZooKeeper directly to a game, so I'm coming up with this on the fly. You could think of assigning one server to handle one server in your application, not a ZooKeeper server, right? So one of your application servers to handle the traffic of a given user. So that could be the master for that user, right? And if you want to make your game fault tolerant, if the master for that user crashes, you don't want your user to be offline as a consequence of that crash, right? So you want to go and allocate another server to deal with that user, and that's where the fault tolerant master election that ZooKeeper provides kicks in.
And so, and this is just to get into a specific question. When you're putting data in these various nodes, and these nodes have to be consistent with one another, how is the data being propagated from znode to znode? Maybe this is a question that would be more appropriate for later in the conversation, but I mean, is it sort of like a gossip type protocol, or how exactly does that work?
No, it's let me start by saying that in a ZooKeeper ensemble, so ensemble is the name we give to the group of servers that is serving a given ZooKeeper instance. Right? So when you connect, you're a client of ZooKeeper, right? So you have an application that binds to the client library, and it connects to an instance of ZooKeeper. That instance is, well, it could be a standalone, but typically for production use, you have a replicated setting. And so that set of replicas, we call it an ensemble. So each of the servers in the ensemble contains a full copy of all the znodes that have been stored in that instance of ZooKeeper. So what we do is, whenever you come and say, create the znode, what the service is going to do is, it's going to propose that we create, that the ensemble creates that znode. And in the case that there is agreement on the creation of that znode, then all servers are going to record it. And so all servers in a ZooKeeper ensemble will contain a copy of that znode. Now, the specific protocol we use is not gossip. We use what we call an atomic broadcast protocol. So it provides stronger guarantees. So it guarantees that all the updates that apply to those replicas, they come in the same order. It does not guarantee, though, that they come at the same time, right? So we do not guarantee that they come at the same time. We only guarantee that they come in the same order. And so all those replicas are going to apply those state updates. State updates being a Z node being created, a Z node being deleted, the data of a Z node being changed. So those are all state updates. And so with this protocol, all those state updates are gonna be fed to all those servers in the same order.
Sure. Okay, and so I guess, zooming out a little and going back to the high level, let's talk a bit about what is and what isn't ZooKeeper. So, I'm trying to, sort of go back and forth between perspectives of people who are a little more familiar with distributed systems and maybe familiar with ZooKeeper, and then people who are less familiar with it. And so maybe for the people who are less familiar, maybe we could put a little more of a definition on what is and what isn't ZooKeeper. Is it a database? Is it a file system? Is it a key value store? How should a developer who comes into a new company and sees, okay, we've got this ZooKeeper thing running, what am I supposed to think about this thing?
So that's why we sort of coined this term coordination service, because it shares properties with all the systems you mentioned, like file systems, key value stores, databases even, but it's none of that. It's again, it shares similarities, but it doesn't. I don't think we can say that ZooKeeper is any of those. So, for example, if I think of key value stores, updates, so you can think of Z nodes in ZooKeeper as a Z node has a path, and so you can look at that as a key, and the data of the Z node can be seen as the value of for that key. But in a typical key value store, you don't try to order updates across keys, or you don't even try to organize to provide a hierarchical organization as we do with C nodes. And this hierarchy turns out to be important, because one of the calls that we have is get children, right? So you get the children of a Z node inside the hierarchy, and that turns out to be very important in many of the recipes that we have. And so in the end, it shares properties with all those classes of systems, but I think it really deserves a name of its own, or a class of its own.
So a distributed coordination system is what you would call it.
Exactly. And in the case of ZooKeeper, we also call it a coordination kernel, because in reality, ZooKeeper does not expose any of the primitives themselves. It doesn't, so if you look at the API, you're not going to see anything about master election. You're not going to see anything about locks. You're not going to see anything about group membership, right? It's about what you can build on top of it, right? So the recipes are a very important part of ZooKeeper, but ZooKeeper itself only provides the kernel that allows you to implement all that.
So because those things are less exposed, things like leader election, does that make it, once you start to, let's say you start to scale a system with ZooKeeper, and maybe you want to loosen certain requirements or tighten certain requirements, are there things that are sort of kept from the user because of the simple API that make it maybe more difficult to fine-tune or perhaps to scale, or is that not really an issue?
I think it's actually the other way around. I think the fact that we have an API that does not expose any of those primitives directly gives the developer more flexibility. One good example is master election. There are at least two different ways of implementing master election that has been used in across applications, right? So if we were to implement master election in a given way, there would be a single way of doing it, right? And because we have this core API that you can build your recipes with, you can think of different ways of doing these tasks. Now, with respect to scalability, the scalability limitations of ZooKeeper are actually related to the core protocol, which is fairly fundamental, and I believe any system that implements this kind of coordination would have the same limitations. But with respect to the API, I think what we did in ZooKeeper is actually a great thing, because it gives flexibility into the implementation of primitives.
Okay, I understand. So you're saying that the things that you do need to access in maybe the underlying API, or maybe beneath the API layer, they essentially are accessible, but it's just you have to get to them through the API.
Yes.
Okay. So let's talk about some specific use cases. What are some ways that you have seen ZooKeeper deployed?
So when you refer to use cases, I can think of the actual recipes that people have used. Like, the examples I can think of with respect to recipes are master election, which is pretty popular, group membership, metadata management, and a lot of the synchronization primitives. I don't know, like locks or barriers, or even if you're just trying to do conditional updates. Right, so you have multiple clients trying to update the same Z node, and you want to make sure that the Z node is updated in a consistent manner. This is fairly abstract, right? So I'm just giving you sort of the tasks and the recipes that people have implemented. Now, if I go one level up and think about the actual applications that have used this, two applications that are fairly popular and come to mind are data stores like HBase and Hadoop. In both HDFS and Yarn, ZooKeeper has been used for high availability. So, for example, for master election and for reliable store.
So, okay, could you maybe provide like higher level? I mean, I definitely understand what you're saying, but maybe you could provide a mapping from some recipes to maybe like business side use cases.
Sure. So let's pick master election. Okay. So let's say that you have a master for your file system, like the name node in HDFS, right? Let's say you want to elect a leader. The simplest way of electing a leader is to establish the path for a master lock, right? Let's call it a master lock. So you go to ZooKeeper and say create / master lock. It doesn't have to have any data at this point. Right, create / master lock, and you could have many clients actually trying to do this, right? Because ZooKeeper again replicates these writes, and all the replicas see this update in the same order. Only one of those clients will be able to create the Z node, right? So one is going to succeed in creating that Z node. Right, and the one that gets okay becomes the master, and so he holds the master lock at that point. All the other ones won't be able to create. They will get an error message saying, this node already exists, and at that point they know that they are not the leader, they're not the masters, and so they have to follow the master or watch the master in the case the master goes away. But then the creation of the Z node is not enough to make your master election fault tolerant, right? The other thing you want to do is you want to create that Z node with the ephemeral flag. The ephemeral flag is a very interesting feature of ZooKeeper because it allows that Z node to be deleted in the case the client goes away. So if, say the client crashes, ZooKeeper is going to determine that because the session of that client is going to expire, and it's going to automatically delete that Z node. So all the other clients that were interested in becoming masters, they will be watching that Z node, and when it's deleted, they will know that it has been deleted, and so they will run another round of master election. Right? So I have done all that with a single Z node, and the features I have used again is one API, which is to create the Z node. I created that Z node as an ephemeral Z node, and the other clients that are not masters, they use the get data Z node to watch the master lock, and they get a notification back when the master lock is deleted. That's one example of a task that you can implement with ZooKeeper, and it's fairly popular, and you can easily map that to a use case like the one I mentioned. You have the head of a file system or of a data store like HBase, and you need to make that fault tolerant.
Okay, that makes sense. And that would be relevant on any distributed database type of system, I guess. Whether you're Facebook that's making a database of billions of people, or some online store that's making a database of all kinds of products, and you need to keep the things consistent. You want one user to be seeing the same sorts of stuff that another user is seeing. that was sort of what I meant by the higher level business case, but I think I understand the mapping. So how big of a cluster do you typically see ZooKeeper deployed across? How am I scaling my ZooKeeper cluster from 10 users to 1,000 users to 1,000,000 to 1,000,000,000? How does that look?
I have seen clusters with thousands of clients talking to the same ZooKeeper ensemble, ensembles of say 5 to 7 servers. The limitation there is mostly the amount of traffic you want to impose on ZooKeeper, right? But the short answer is that so you can have clusters of hundreds to thousands of clients connecting to a ZooKeeper ensemble of say 5 to 7 ZooKeeper servers. That's a pretty typical case.
And is it accurate to say that ZooKeeper is strong for systems with lots of reads and fewer writes?
Yes, indeed. So writes, as I explained before, writes require to run this atomic broadcast protocol, which is essentially writing that state update to all replicas. In fact, we just need to wait for a quorum to respond, but we do send the write to everyone. But the reads are served locally, right? So if I add more servers to my ensemble, then I can definitely increase my read capacity, not my write capacity though. So it's a system that is highly targeted to read dominated workloads. Although it does pretty well on writes as well. I mean, we can easily get these days 20,000 writes per second with the implementation we have. So it's not that the volume of writes has to be small. It's just that we cannot really scale it at this point. So if you want to go from 20,000 to say 100,000 and eventually to 1,000,000, then there's no way in ZooKeeper today to actually do this. But for the reads, it can increase as much as you want.
So how big of a problem is this? Like, have there been users that have said, like, oh, we actually can't use ZooKeeper because it doesn't let us write aggressively enough? Or do people end up using an alternative service if they need some amount of writes like that?
The interesting thing is that most cases I have seen where people were requesting exactly what you said, so I want to be able to scale write workloads. ZooKeeper is actually not a good fit for that. So a good, at a high level, good use case for ZooKeeper is one in which the writes to ZooKeeper are not in the critical path of your application. So if everything that comes through your system, every change that comes through your system is written to ZooKeeper, that's probably not the right thing to do. You probably need some sort of data store, some key value store to handle that kind of workload. ZooKeeper is really for the meta operations I was mentioning before. And so those operations, so often what happens is you have one write to say some metadata element, right? So let's say that you have some metadata that your cluster needs to know, right? So you update that metadata, update the value of those variables, and by updating some znode, right? But you expect all the servers in your cluster to read it. So that translates into one write and say thousands of reads, right? So this is a fairly common use case for ZooKeeper.
Sure. Okay, so let's look at a little bit of history of ZooKeeper. So ZooKeeper began at Yahoo and eventually was moved to Apache as part of the Hadoop project. So I'd like to talk a bit about why ZooKeeper was so important to Hadoop.
That's a very interesting question. In fact, it wasn't important to Hadoop at the time. I think we ended up as a sub-project of Hadoop because the Hadoop community was in general supportive of the project. And there was also this perception that HDFS and ZooKeeper were supposed to have a similar relation to GFS and Chubby. But ZooKeeper at the time was not used by Hadoop at all.
Oh, okay. So, but eventually it's become an important part of the Hadoop, correct?
Yeah, but only after we left. After it became a top level project, sometime later, they started using it for a name node HA, and today you have yarn as well, relying on ZooKeeper.
Okay, could you maybe give some color on the integration of that? Like, how is ZooKeeper the best solution for that purpose of Hadoop?
So if it's the use cases I mentioned before, so master election, storing metadata reliably, these are the things that they are looking for in those use cases. And so ZooKeeper is in that ecosystem. It's a fairly stable project. It's battle tested, so it's definitely a good element, a good component to be in that role.
Okay, that makes sense. Let's drill down a little bit into the different roles in a ZooKeeper implementation. So you have the roles of followers, leaders, well, a leader at least, clients, and observers. So let's talk about the abilities and the responsibilities for the roles.
Sure. Let me start with clients. So clients connect to a single server at a time, right? So even if you have many multiple replicas, even if you have replicas of the system, the client's going to connect to a single server at a time. So out of those servers, one is the leader, as you mentioned, and the others could be followers or observers. The leader processes all requests that change the state. So if a client submits say a create Z node, that's going to go to the leader. The leader is going to produce a transaction, which is a state update. It's going to propose that to the followers. The followers are going to persist that on disk. They're going to acknowledge to the leader, and then the leader is ready to commit. Followers are different from observers. So observers do not vote in that process I just mentioned. Observers, they just learn the state changes, right? The state changes have been committed. And by doing that, the main thing we achieve is that we can increase read capacity without actually increasing the work the servers have to do for a given state change. What else can I say? So going back to the leader proposing a state change, when he receives a response from a majority, then he's ready to respond to the client. And at that point, the client receives a response back, and that's more or less how the flow works of requests in ZooKeeper.
Okay, yeah, sure. So that makes sense. So is there a specific algorithm that the consensus protocol for ZooKeeper is based on? Like, is it sort of like a Paxos type of consensus, or is it maybe like based on Raft, or is there not a close relationship between the way that ZooKeeper maintains consensus and the way that these things are outlined in academic papers?
Right. So the protocol we use is called ZAB, which stands for ZooKeeper Atomic Broadcast. It has elements that differ from Paxos, although you can go through this exercise of mapping Paxos somehow to ZAB. But by reading the two papers, you notice that there are differences. And the difference is mainly because of the way we have structured the components of the service, leaders and followers, by propagating the state updates and having this dependence between the sequence of between state changes in the same sequence, which sort of forces us to stop the consensus protocol during a leader change, so that we could guarantee the consistency of the service. So it is a protocol that's called ZAB. It has many elements in common with Raft. Raft actually came a few years later, and that's the protocol we used. But again, both Raft and ZAB have elements of earlier protocols like Paxos.
I'm sorry, could you repeat again what the differentiating requirement that incentivized you to make your own protocol?
We have this need of when we do a leader change, we need to have agreement on the initial state of the new epoch. Okay, so the protocol is structured in epochs, right? So you have a leader comes, proposes a bunch of things, a bunch of state changes, those are committed, and at some point that leader goes away, it crashed or it got suspected of crashing, and then a new leader comes. So when that new leader comes, before it can start proposing new state changes, it needs to agree with the other servers what the initial state of the new epoch is. And so that required us to come up with a different protocol.
Okay, yeah, I understand. So I know that implementing anything in a distributed system can be hard, or implementing a distributed system can be hard specifically. So how did you perform validation and testing on ZooKeeper? And how did you achieve a level of confidence in the correct behavior? Because, anytime you're trying to implement a distributed feature of something, if you want to test it, there's always sort of the question of, if I test this on 3 servers, is that equivalent to how it operates on 5 servers? Is that equivalent to how it operates on 10 servers? And so on. So how did you do this validation and testing?
It's a combination of reasoning and writing real tests. So we did a lot of reasoning about not only the code, but the protocols behind it. And we have a lot of tests. So in Apache in general, I won't generalize to Apache, but in ZooKeeper, we use extensively JUnit tests to test cases that could be problematic or that have been problematic in the past. And then anytime a change goes in, is checked in, we have to run those tests to make sure that it's not, that it's not violating or it's not breaking anything that's already in there. And there is also the test of time, right? It has been running production a number of places for a long time. This is not to say that there is no bug, right? Or there has never been bugs. Quite the other way around. We always find small things that we can fix, and that's part of the work of the community. Fix these bugs that we find every now and then. But in general, I would say that the customers of ZooKeeper are really happy with it. Over the years, we have heard lots of good comments about the stability of ZooKeeper and how well it runs and so on.
Are there any known edge cases that result in failure?
Edge cases that result in failure. So could you be a bit more specific about failure?
I guess I was unspecific on purpose because I wanted to see if that evoked any. Is there anything that happens frequently? Maybe because it could be just because people tend to implement something in an erroneous way, and it leads to a vulnerability at an edge case, or maybe it's something that is inherent in ZooKeeper that leads to an edge case. I'm just curious as to what, or how you would define failures and the edge cases that would result in those.
Right. Well, I guess I can see failures then in 2 ways. One is, for example, if we ignore the notifications that ZooKeeper sends up to the application. Right. So one example is if you're implementing master election. Well, let me actually step back and talk about sessions a bit. So when a client starts talking to an ensemble, he has to establish a session. Right. A session can live through multiple connections. So initially, the client connects to a server, but later on, that client may move that session to a different server, right? Disconnects from the first server, connects to a new server, but the session is still the same. If you're implementing master election, what we strongly recommend is that if you disconnect from a server, right, and you receive that notification from the client library, the master should stop doing any kind of master work. Because at that point, it doesn't know what the state of the cluster is. It might be the case that its session has expired, right? Or it's going to expire soon. And in that case, it could be, its decisions or its steps might be conflicting with the steps of the new master, right? And this is something that is problematic. So the bottom line is ignoring the notifications that the client library sends up is a bad idea, and doing that could lead to say bad cases in your application. There are failures on say the operational side of ZooKeeper. So ZooKeeper today is sensitive to losing disk state. It heavily depends on servers not losing disk state to guarantee the consistency of the data. This is not to say that there is no way around it. So if a server loses its disk state, then you need to remove that server from the ensemble and reinsert it to guarantee that there is no consistency problem. This is an argument, sort of a deeper argument into the protocol. But at a high level, this is what happens.
And so if I'm a user that's implemented my ZooKeeper system, do people typically do fuzz testing, or is there a barrage of random and unusual events that you can just impose on the system as a means of testing it?
So as I mentioned, we run JUnit tests, right? And that we are continuously running it, and every time we check in that, we also need to run it before it's checked in. Users of ZooKeeper tend to have their own set, especially the big customers of ZooKeeper. They tend to have their own set of tests. At some point, we talked about fault injection. This is not present in ZooKeeper today. So I think the short answer to your question is that we don't have anything like you're suggesting, although we have various test cases and test suites that the various customers run on ZooKeeper distributions.
Okay. I want to talk about the cap theorem. What is your definition of cap, and do you actually find it useful? Do you follow it as a design principle? And could you elaborate on consistency, availability, and partition tolerance?
Right. So the cap work is a bit old by now, and in the past few years, a few people have actually criticized it, trying to uncover some of the dangers of using the cap definitions loosely. On my end, I would say the cap has always confused me a bit, mainly because it defines terminology in a way that is very different from the way I typically use. So if I think about ZooKeeper, I would actually say that it's consistent, it's available, and it's partition tolerant. It's consistent because it relies on this atomic broadcast primitive, which makes sure that the state updates are totally ordered and delivered in order to the server replicas. It's available because a single crash or a minority of the server replicas being unavailable is not going to cause the whole system to be unavailable. So availability is about the total amount of time that the service as a whole is up. And finally, it's partition tolerant because it does not admit split brain. So split brain is a situation in which two or more parts of the system end up making progress independently, which causes the state in which of those parts to diverge when compared to the others, which is clearly bad, at least in the case of ZooKeeper. Now, if going back to the cap, to the cap work, cap, as many people expose, is essentially says that we have these three properties, and when we're building a distributed system, we pick two. So CP, CA, or AP. I would say that CA doesn't make a lot of sense because CA essentially assumes that partitions do not occur. Well, I'm not sure how one can control whether partitions occur or not. I think the best one could do is to assume that partitions won't occur. In the case they occur, you just suffer the consequences. But I'm not sure how much one has to gain by just doing this. Doesn't sound like a great way of thinking about systems.
Does ZooKeeper fall cleanly into any of the models provided by CAP, CP, CA, or AP?
Being strict about the CAP definitions, ZooKeeper is really none of those. So the workload isn't necessarily linearizable because the regular reads, so the basic reads we have, they do not make the workload really linearizable, so it's not consistent. And it doesn't accept split brain. It doesn't admit split brain, so it's not available either. But quorum-based systems, replicated state machines, which ZooKeeper is an instance of, typically fall into the category of CP, consistent and partition tolerance. So that's really the closest to ZooKeeper.
How useful is CAP when it comes to trying to reason about systems?
One of the great benefits of CAP is that it provides a common terminology for people to talk about their systems. But I really think that is great only to start conversations. So are you a CP person or are you a AP person? But thinking deeply about systems and its relation to CAP seems a bit pointless to me. Now, I think the CAP work is very relevant. So if you read the CAP proof, the CAP theorem proof, it's very interesting. It provides a lot of insight, but it's a really narrow result. although people keep using it in a fairly broad manner. Just to give an example, so if I think about consistency, and if I pick the definitions in the distributed systems by Andy Tannenbaum, so over there are over 10 definitions of consistency, and so narrowing it down to just linearizability doesn't sound very wise to me. Although granted that linearizability is a very important property for many of the systems that we build and use.
Would it make sense to extend the CAP theorem to try to define more finer-grained classifications for systems? Because these three dimensions, C, A, and P, consistency, availability, and partition tolerance, they don't seem to capture the richness of systems these days. I mean, maybe they do provide a framework in which you can write a proof, but maybe that's not as useful as having a more rich terminology.
Yeah, as I said, I think one of the interesting and nice things of the CAP work is that it has achieved to create a common, simple terminology that developers of distributed data systems have been using to discuss our projects. I don't think everyone doing distributed systems fully understands the implications of the CAP definitions, though. And so, if we are to come up with something different, I think this new thing should have it should make a bit more clear what consistency, availability, and partition tolerance, or whatever other terms we come up with are, so that developers or distributed systems builders do not end up using these terms loosely and misinterpreting what's actually going on just by using terminology loosely. But at the same time, as I mentioned, I don't think such a small narrow terminology or such a concise model is great for something else other than just starting a conversation. I really think that when we talk about systems, there are just so many subtleties and nuances to the things we do that you need to go deeper to understand what needs to be done, what kind of properties you're looking for, and so on. As I was making this reference to consistency properties, there are many consistency properties one could think of when implementing a system, and so just thinking about one or maybe two, that doesn't sound great. So a terminology that allows us to convey in a concise manner, but in a precise manner as well, what we're trying to do in a project, that wouldn't be a bad idea. But again, keeping in mind that down the road we need to talk in more detail about things so that we can think more deeply about what we're trying to achieve.
So how does ZooKeeper guarantee that clients will never detect old data?
ZooKeeper actually doesn't make that promise. What ZooKeeper tries to do is actually to avoid discussions about time altogether. So the replicas guarantee that state changes come in the same order. Also, it guarantees that replicas receive the state changes in the same order. But it doesn't really guarantee that a client is going to read some older data. Right? So it could happen in a system that that at some point in time, two clients read different values for the same znode. But over time, right, the client that reads the older data eventually will be able to see that state update, right, the newer version of the data. So ZooKeeper guarantees the order of updates, but not when they're going to happen.
Right. And so ZooKeeper keeps watch over something that sort of looks like a file system in some sense. And I'm curious, are the observers costly? Like, or is the notion of observing this file system, is it costly? Like, are you just constantly polling and spending energy? And this question may lend itself to, maybe I still have kind of a loose understanding of how ZooKeeper works, but maybe you could address that question.
Sure. So when a client sets a watch on a znode, right, say, I want to receive a notification when something happens to this znode. And so that request goes to ZooKeeper and to the servers, and the server that receives that request annotates that particular path for that watch. And so when it receives the update, it triggers the notification to the client. So the client has to do no work on that watch, right, while it's connected to that server. And when the state change comes in, the server will produce a notification and ship it to the client. The burden is mostly on the server side.
Okay. How horizontally scalable is ZooKeeper? If I'm growing, how rapidly can I just throw new servers on ZooKeeper and say, hey, rebalance this, or is it more of a complicated, difficult process?
If you're trying to scale writes or the amount of state of a ZooKeeper ensemble, then we don't have any good mechanisms for doing this today. What you can scale, horizontally scale in ZooKeeper today is read capacity. Right, as I was mentioning, you can throw in more observers or just increase the number of followers, and that will increase your ability of doing reads. Right, you can do more reads per second. Okay,
makes sense. So I guess we can start to close off. I'm curious about where ZooKeeper is going. So what is the future? Are there features that need to be implemented? Are there changes that need to be made or that are going to be made? New features being added?
The main feature we have been working on recently is reconfiguration. This is it has been made recently available in the 3.5 branch, which was released in August, if I'm not mistaken. But that branch is not stable yet, and so the community has been focusing a lot on that feature.
Okay. For somebody that's getting started on ZooKeeper, what would you say are the best resources to consider? I know you've mentioned the recipes several times, and certainly we'll link to some of those and how to pursue them. But what are some other resources that people should look at, and maybe other projects that people should look at?
Right. So the Apache Curator project is definitely a very good source of not only information, but you can actually use the recipes that they have implemented. So Apache Curator, the proposal of Curator is to implement the best practices known for ZooKeeper. And so you can learn a lot by just looking at the recipes, and you can even be a bit lazy and just use them directly. And so it's definitely a good source of recipes, right? And knowledge about how to program against ZooKeeper.
Great. And how can people find out more about you or follow you on social media?
Oh yeah, so I have a Twitter account. It's FP Junqueira. So that's my handle on Twitter. I'm also on LinkedIn. So if you search me for my name, you'll probably find it. And so those are good ways of following me. And I also strongly encourage the ones interested in ZooKeeper or learning about ZooKeeper or contributing to ZooKeeper to sign up for the list, for the dev list and the user list. We're always interested in onboarding new contributors, new committers, and growing the community. So I would be happy to see more people signing up.
All right.
And talking to us in Apache.
Okay, well that's great. Flavio, I want to thank you for coming on Software Engineering Radio.
Thanks for inviting me.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more information about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can write comments on each episode on the website or write a review on iTunes. Mention or message us on Twitter at SE Radio, or search for the Software Engineering Radio Group on LinkedIn, Google+, or Facebook. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under the Creative Commons 2.5 license. Thanks again for your support.